Hey everyone, welcome back to the Incredible India podcast series. I am Sam, and joining me today is my co-host, Taylor.
Hey, Sam, really glad to be here. We have an absolutely wild story to get into today.
We really do. So I want you to picture a scene for a second. It is 1924.
Okay.
And you are a 30-year-old university professor, right?
Yeah.
You're sitting in this sweltering classroom in Dhaka, in colonial India.
Right, setting the scene.
Yeah. And you have just received a letter from a prestigious European scientific journal. And it is a rejection.
Ouch.
Right. They are basically telling you that your math is completely wrong. You're trying to challenge the greatest, most established minds in physics, and the entire establishment is just shutting the door in your face.
Which, for most people, that's the end of the road.
Exactly. Most people would just file that paper away in a desk drawer and move on with their lives.
Yeah.
But this professor didn't. He took this massive, kind of audacious leap of faith that ultimately laid the groundwork for, arguably, the most important physics discovery of our century.
The Higgs boson.
Yes, the Higgs boson, also known as the God particle.
It really is one of the greatest what-if moments in modern science. And, our mission for this deep dive today is to explore this fascinating article from 5 Census Tours. It digs into the life of Satyendra Nath Bose.
Right, the guy who effectively rewired how humanity understands the universe.
Yeah. And yet, if you ask someone on the street outside of India who Bose is, you will almost certainly just get a blank stare.
Which is completely crazy to me, considering, almost half the fundamental particles in the universe literally bear his name.
It is wild. But to figure out how this obscure professor managed to upend quantum mechanics, we can't just start with that rejection letter in 1924.
No, because I always get annoyed by that persistent myth of the solitary genius.
Oh, for sure.
The whole idea of someone sitting alone in a dark room until a light bulb just magically turns on. Genius requires an ecosystem. So
Yeah.
Where did this guy even come from?
You're entirely right to question that solitary genius narrative. It almost never actually happens that way. To understand Bose, you really have to look at the intellectual crucible that forged him.
Okay, so where do we start?
Well, he was born in Kolkata in 1894, and he eventually studied at Presidency College, which was built way back in 1875. And the timing and the location here, they're critical.
Because of the Bengali Renaissance, right?
Exactly. This was the absolute zenith of the Bengali Renaissance. Presidency College wasn't just some local school. It was easily one of the most intellectually electrifying hubs in all of Asia at the time.
Yeah, the article really paints a picture. When you look at the people walking the halls of that college, it actually reminds me of those legendary sports dynasties.
Oh, like what?
I grew up obsessing over the 1990s Chicago Bulls. And the thing about those teams is that you don't just have Michael Jordan playing in a vacuum, right?
Right, you've got the whole roster.
Yeah, you have Scottie Pippen, you have Dennis Rodman, Phil Jackson coaching. You have this entire ecosystem of just absolute brilliance where everyone is fiercely competing and pushing each other to completely redefine the game.
I like that. That ecosystem is exactly what Bose had, but, for physics and chemistry.
Right.
The faculty and the student body there, they were pushing the boundaries of human knowledge literally on a daily basis. I mean, one of Bose's professors was Jagadish Chandra Bose.
Oh, wait, the radio guy?
Yes! This is a man who successfully transmitted the world's first wireless microwave radio signal, and he did it a full year before Guglielmo Marconi.
Who usually gets all the credit in the Western history books, obviously.
Exactly. And then another mentor of his was Prafulla Chandra, who was this visionary chemist who practically willed India's pharmaceutical industry into existence single-handedly.
Wow.
And sitting right next to Bose in class, like his literal classmate, was Meghnad Saha. He's the student who would soon develop the ionization equation that completely transformed how we understand the temperature of stars.
Okay, when you lay it out like that, it actually explains so much about his mindset later on.
How so?
Well, if your daily reality is watching your teachers and your classmates invent new scientific fields and constantly prove the European establishment wrong, suddenly the establishment doesn't seem so intimidating, right?
Yeah, that's a great point.
You're effectively immunized against imposter syndrome. So how did that localized confidence play out for him?
Well, it's the only way to explain what happens next. So by the early 1920s, Bose is working as a reader at the University of Dhaka.
Okay.
And he's trying to prepare a lecture for his students on Max Planck's law of electromagnetic radiation.
Which is a huge deal. That's the foundational math for early quantum mechanics, right?
Right. It describes how objects emit heat and light. But as Bose is preparing his notes for this lecture, he gets deeply frustrated.
because the math didn't actually work on its own terms.
Exactly.
The source mentions that to make the equations balance, all these top European physicists were subtly relying on older concepts from classical physics.
Yeah, they were cheating the math a little bit.
It's like trying to build a modern smartphone but having to stick a wind-up gear inside it just to make it turn on. Bose wanted a pure, unified theory. He wanted to use only quantum mechanics.
Right, because classical physics treats energy as a continuous wave, like a smooth flow of water. But quantum mechanics says energy comes in distinct, separate packets. Quantum.
You can't logically mix those two things.
You really can't. So to get rid of that classical scaffolding, Bose had to propose something that sounded like absolute madness to physicists at the time.
Wait on me.
He suggested that fundamental particles of light, which are photons, are genuinely and fundamentally indistinguishable from one another.
Okay, wait, stop right there, because this is where my brain starts to hurt a little bit.
It's tricky, yeah.
What does it actually mean for two things to be fundamentally indistinguishable? I mean, if I have two identical twins standing in front of me, I can still point and say, that's twin A and that's twin B. They occupy different physical spaces.
And that right there is the bias of living in the macroscopic world. We're used to big objects.
Fair enough.
Think about a thought experiment. Imagine you have a red marble and a blue marble. If you roll them on a table, you can easily track which is which, right?
Right.
Now imagine two completely identical red marbles. Even if they look exactly the same, your brain tracks them by their physical coordinates, the marble on the left and the marble on the right.
Because they refuse to share the exact same space. The marble on the left can't physically overlap with the one on the right.
Exactly. Our entire intuitive understanding of reality relies on the idea that objects have a unique identity based on where they are. But Bose realized that in the quantum realm, photons do not behave like marbles.
Oh, wow.
They don't have individual identities, and more importantly, they do not insist on personal space.
So you literally cannot track photon A versus photon B.
No. Because they don't demand unique coordinates, they can just crowd together into the exact same quantum state. And if you change the fundamental way you count these particles based on that crowding behavior, suddenly Planck's math works perfectly out of pure quantum mechanics.
No classical wind-up gears required.
None at all.
It's just an incredible conceptual leap.
Yeah.
So he writes up this massive breakthrough, he translates it to English, and submits it to the Philosophical Magazine in late 1923.
And here we are back in Dhaka.
Right, back to that sweaty room. 6 months go by, and the journal rejects it. They essentially tell him his fundamental premise is completely flawed.
Which must have been devastating.
But what does he do? On June 4th, 1924, he takes his manuscript, writes a cover letter that begins with, "Respected sir, I am anxious to know what you think of it," and he just drops it in the mail.
Directly to Albert Einstein in Berlin.
Yeah. He essentially asked the most famous scientist on the planet to read it, translate it into German, and get it published for him.
It is pure, unfiltered audacity. I mean, the European Physics Centers barely even knew the University of Dhaka existed. It's an unsolicited letter from an unknown colonial academic.
It's honestly like some unknown kid recording a demo track in his garage, getting rejected by the local college radio station, and then just deciding to mail the cassette tape directly to Paul McCartney.
Oh, yes.
And McCartney actually listens to it, calls him up, and says, "This is brilliant. I'm going to produce it myself."
That is a perfect way to frame it. Because Einstein didn't care about credentials, he cared about ideas. Einstein read the math, and the light bulb just went off. He saw immediately that Bose was right.
That's so cool.
He personally translated the paper into German and leveraged his immense influence to get it published in the Zeitschrift für Physik, which was the top physics journal of the era. He even sent Bose a postcard that July calling his work an important step forward.
But Einstein didn't just do Bose a favor, right? He recognized that Bose had fundamentally changed how we categorize the universe itself.
Yes. Einstein realized Bose had accidentally drafted a completely new classification system for reality. Because of that rejected paper, modern physics now dictates that absolutely everything in the cosmos falls into one of two categories. There is no third option.
Everything is either a fermion or a boson.
Exactly.
Let's break down that binary, because it's so fundamental to how reality actually holds together. Let's start with fermions. What makes a fermion a fermion?
Okay, so fermions are the building blocks. They obey a rule called the Pauli exclusion principle.
Which means what, exactly?
It's a fancy way of saying they strictly demand their own personal space. They absolutely cannot occupy the same quantum state at the same time. Electrons are fermions, Quarks, which combine to form protons and neutrons, are fermions.
So they're the marbles.
Right. Because they refuse to overlap, they are forced to stack up and take up physical volume. That stubbornness is literally what gives matter its solid, rigid structure. You, me, the microphone in front of you, it's all solid because fermions refuse to share space.
So if fermions are the actual bricks making up the physical universe, that means the other half, the bosons, named after our guy in Dhaka, must be the mortar holding those bricks together.
That's a good way to look at it, yeah.
But based on what you said earlier about photons crowding together, this has to be some deeply weird mortar.
Oh, it is exceptionally weird mortar. Bosons do not obey the Pauli exclusion principle. They obey Bose-Einstein statistics. Because they don't demand personal space, you can pack an infinite number of bosons into the exact same space.
Infinite.
Infinite. They don't make up solid matter, they carry forces. Photons carry the electromagnetic force. Gluons, which hold the nucleus of an atom together, are bosons. You can put infinite mortar in the same spot, and instead of pushing the bricks apart, it just compounds the strength of the force.
That distinction completely blows my mind. And it perfectly sets up what happened decades later, right? Because this framework is what eventually led us to CERN in Geneva on July 4, 2012.
Ah, yes, the big announcement.
When the global scientific community announced they had found a brand new boson, the Higgs boson, the so-called God particle.
The elusive final piece of the puzzle. Back in 1964, a British physicist named Peter Higgs theorized a specific type of boson. It was associated with an invisible energy field stretching across the entire universe, which we now call the Higgs field.
And how does that field actually work in relation to all those fermion bricks we just talked about?
Think of the Higgs field like a thick, microscopic syrup permeating everywhere.
Okay, syrup.
Right. When certain fundamental particles try to move through this field, the Higgs bosons interact with them, creating drag. And we perceive that drag as mass.
Wait, so without it?
Without the Higgs boson, particles would just zip around the universe forever at the speed of light. They would never slow down enough to clump together. That means no mass, no atoms, no stars, no planets, and definitely no humans.
Which completely explains the dramatic nickname.
The God particle.
Yeah, Leon Letterman coined that in a book in 1993, and the media just ran with it. But it's absolutely nothing to do with religion, right? It's just a shorthand way of saying that without this specific boson, physical reality as we experience it simply cannot exist.
Exactly. But, here's the massive irony of the God particle dominating all the headlines. The everyday, highly practical behavior of Bose's particles is actually what makes your modern life function right now.
Oh, really?
Yeah, the math Bose worked out in 1924 is the hidden engine of modern technology.
Let's dig into that, because the jump from theoretical quantum math to stuff I use in my living room is fascinating. The deep dive mentions lasers, which I never really thought about how a laser pointer actually works.
Well, it relies entirely on Bose's concept of indistinguishability. Normal light, like from a regular light bulb, is chaotic. It's a bunch of photons bouncing around at different frequencies, just scattering everywhere.
Right.
But because photons are bosons and can share the exact same quantum state, you can stimulate them to march in perfect synchronized lockstep.
Oh.
Yeah, they become a single, coherent, highly concentrated beam of light. A laser is literally just Bose's math in physical form. If photons were fermions, lasers would be physically impossible.
That's incredible. And it's not just light, right? It scales up to things like medical imaging. Like, if anyone listening has ever had to get an MRI at a hospital, you're relying on this science.
Absolutely.
The source notes that the superconducting magnets in MRI machines have to operate with zero electrical resistance. And the way they achieve that is by cooling the materials down to such an extreme degree that electrons, which are normally fermions that bounce off each other, they actually pair up.
Yeah.
And when they form a pair, they effectively act like a boson. They stop fighting for space and just glide through the wire seamlessly.
That cooling concept is actually where Einstein took Bose's work next. After Einstein got the paper published, he realized you could apply Bose's statistics to whole atoms, not just light.
The whole atoms.
Yeah, he predicted a theoretical fifth state of matter. We all know about solids, liquids, gases, and plasmas. But Einstein predicted something called a Bose-Einstein condensate, or BEC.
Okay, walk me through the mechanics of a BEC. How do you get a bunch of separate atoms to turn into a new state of matter?
It's all about manipulating temperature. Temperature is really just a measurement of how fast atoms are jiggling around. At room temperature, atoms act like a swarm of angry bees, chaotic, bumping into each other, maintaining their distinct identities.
Like the marbles.
Right. But Einstein hypothesized that if you take a specific type of bosonic atom and cool it down to just a fraction of a degree above absolute zero, the jiggling almost entirely stops.
So they lose their momentum.
Right. And in quantum mechanics, when particles lose momentum, their quantum waveforms literally spread out. As they get colder and colder, these individual atomic waves expand until they begin to overlap.
Oh, so they lose their individual identities.
Exactly. They lose them completely. The swarm of bees suddenly becomes one single synchronized flock of birds. Thousands of atoms merge into a giant superatom that behaves as a single wave.
That is deeply unsettling and very cool. And that remained purely theoretical until 1995, right?
Yeah, it took 70 years for our laboratory technology to get sophisticated enough to actually cool atoms down that far and prove the math right. Today, those Bose-Einstein condensates are the backbone of quantum computers and the ultra-precise atomic clocks that make global GPS networks function.
But this brings me to a really frustrating part of the story. The scientists who finally produced the BEC in 1995, they won the Nobel Prize in 2001. By some counts, at least 10 different scientists have won Nobels for discoveries rooted directly in Bose-Einstein statistics.
Yeah, it's a sore subject.
Because Satyendra Nath Bose himself never got the call from Stockholm.
It's a massive point of contention. The Indian government has pointed out this oversight many, many times. The Nobel Committee just has a long history of rewarding tangible experimental discoveries rather than foundational statistical frameworks.
See, I struggle with that logic. It almost feels like, okay, if you invent the alphabet, you don't get the literary prize for writing the great novel, even though the novel couldn't exist without you.
That's exactly it.
Doesn't that highlight a massive blind spot in how the scientific community measures real contribution? Like, we prioritize the person who placed the final brick over the person who invented the mortar.
That analogy hits the nail on the head. The Nobel Committee tends to prefer neatly packaged discoveries that can be pointed to in a lab. Bose's contribution was so foundational, so deeply baked into the underlying code of reality, that it ironically became harder to hand him a single medal for it. It was just everywhere at once.
Well, even if the Nobel Committee missed the boat, the global physics community today absolutely knows what they owe him, especially when you look at the frontiers of modern science, like CERN.
Oh, without question. If you go to the Large Hadron Collider today, you know, that 27-kilometer circular tunnel buried deep underground near Geneva where they smash particles together to recreate the Big Bang, you will find an incredibly deep connection to India.
Really?
Yeah, there are over 100 Indian scientists working round the clock at CERN right now. India is an official member state. The spokesperson for CERN, Paolo Giubilino, literally called India a historic father of the entire project. It's a living legacy.
And when you zoom out even further, relying on the context provided by 5 census tours, you realize that Satyendra Nath Bose is not a fluke.
Not at all.
We're so conditioned to trace the entire history of science in a straight line from the ancient Greeks straight to the European Enlightenment, directly to Silicon Valley. But this deep dive totally shatters that illusion. There is a staggering, continuous, parallel track of ancient Indian science that stretches back thousands of years.
The historical record is truly humbling when you look at it. Take atomic theory. Most of us are taught that John Dalton proposed modern atomic theory in the 1800s. But 2,600 years ago, in Gujarat, a philosopher named Canada was proposing a deeply complex atomic model.
Wait, how do you deduce atoms 2,600 years ago without a microscope?
Through rigorous thought experiments. Canada essentially argued that if you take a piece of matter, say a clod of dirt, and keep dividing it in half, you will eventually reach a particle that cannot be divided any further without losing its fundamental properties.
So he just reasoned his way there.
Exactly. He called it Anu. He built an entire conceptual framework around how these indivisible particles combine.
That's brilliant logic.
Yeah.
And the article mentions mathematics in Kerala too, right?
Yes, the Kerala School of Astronomy and Mathematics. In the 14th century, a mathematician named Madhava was studying the stars and realized that classical geometry just wasn't enough to track planetary movements. So he invented infinite series for trigonometric functions.
Wow.
He was essentially doing foundational calculus a full 2 centuries before Isaac Newton and Gottfried Leibniz were even born.
And my personal favorite example from the source material involves linguistics.
Oh, Panini.
Yeah, Panini. Living in ancient India, he built a formal grammar for the Sanskrit language. But he didn't just write a dictionary. He created this massive set of meta-rules that could generate any valid Sanskrit sentence without a shred of ambiguity.
It's basically code.
Exactly. Fast forward to the 20th century, and computer scientists looked at Panini's structure and realized it functioned exactly like an algorithmic compiler. His ancient linguistic rules are fundamentally the same logic structures we use to write modern computer coding languages today.
It entirely reframes how we view human progress. When we look at the discovery of the God particle, we aren't just looking at a modern Swiss laboratory. We are tracing an intellectual lineage that runs straight through the humid corridors of Presidency College in Kolkata, drawing on a tradition of questioning reality that dates back millennia. Bose was just one spectacular link in a very, very long chain.
It just proves that knowledge isn't bound by geography.
Mm-hmm.
The universe reveals its secrets to whoever has the audacity to ask the right questions and honestly ignore the establishment telling them they're wrong. So to bring this all back to where we started, one single piece of paper, written by a frustrated professor in Dhaka, rejected by the gatekeepers, and mailed in sheer desperation to Berlin in 1924. That one paper shifted our understanding of quantum reality, gave us lasers, made GPS possible, and provided the vocabulary to discover the God particle itself.
It's an incredible legacy.
It makes you wonder, what other world-changing ideas are currently sitting in a rejection pile somewhere right now, just waiting for someone to look closely enough to realize they hold the secrets of the universe. Give that a thought the next time you hear a no.
That's a great thought to leave on.
If you decide to travel to India, we have a recommendation. Five Senses Tours organizes tours across India, which are immersive cultural experiences. You can email contact@fivesensestours.com. Note 5 is written as a numeral in contact at fivesensestours.com. Or WhatsApp to +919-845-677-446.